going to introduce the last sort of full-time speaker of the day, Bartosz Szurgot. He's been with Code Dive since the very beginning, so it's his third time. That's why I think we can safely call him our full-time speaker. So he's back, obviously, by popular demand. People find his talks really interesting, his slides extremely funny, and his sense of humor irresistible. He's a man of 1,000 faces. He's a coder, he's a 3D printer, he's a hacker, and a geek, of course. His professional life includes C++, Linux, and embedded. And again, I was trying to dig out something personal about Bartek, and just by accident, I spoke to one of his colleagues. And he said, you know, when I was writing my code, I wrote sort of 30 lines, and then I asked Bartek to consult on this. And in these 30 lines, Bartek found 40 ways of doing it better. That's the expertise we are dealing with, ladies and gentlemen. And also this afternoon, I heard a nickname about Bartosz, but before I tell you what the nickname is, can I ask you, I mean, how are you with dangerous situations? Do you normally keep your cool? Do you panic? Can you keep your cool in dangerous situations? Okay, let's try it. I mean, the reason I'm asking is that Bartek has been described to me as, quote, dynamite. So just in case, may I ask? You should have your special seat belts in your chairs. Can you see them? Yeah. If you don't, imagine you've got them and make sure that you fasten your seat belts, because I'm going to introduce taming software, including, of course, C++ and embedded, by Bartosz Szurgot.
So hello everyone, welcome to the taming of the software, obviously featuring C++, some embedded stuff and more. I'm Bartosz Szurgot, but I usually just refer to myself as Bash, the nickname, because it's first short, easy, and easier to pronounce by foreigners. So most of the time I'm writing software in C++, and this is like my daily work. I also use Linux daily, so I write a lot of shell scripts in Bash. And from time to time do some Python coding, and over time usually a microcontroller electronics. And since recently I do a lot of presentations, actually LaTeX became a tool of my choice as well. So you can say that most of the time just like geeking around. And in my spare time, I provide human race with groundbreaking innovation like the wall-mounted 3D printed tablet holder for your toilet. It's really awesome, give it a try. Yeah, but no worries, this is not what we're gonna talk about today. Instead, we're gonna talk about something completely different. We're gonna talk about software. So, we'll be building, decomposing, abstracting, and testing. Does it sound familiar to you? Yeah, sure, yeah, software developers as well, so you do this on a daily basis. So the first and obvious question is, if it's so omnipresent and everyone does that, then why even bother to talk about that? Well, actually, my observation is that in majority of the projects, the way things are organized actually remind me of an old cartoon when one of the main characters used to say, well, isn't it cute? But it's wrong. You know, the thing is that people have this tendency to reinvent the wheel. And when wheel gets reinvented, it usually turns out to be square. And this makes developers sad, and over time causes a lot of confusion in the project, and over time more and more. So today, we'll be talking about road signs. I will give you a set of battle-tested advices on how to deal with these common problems and hopefully push your project into the right direction. Let's start with builds. We'll have this little pet project, some weather station connected to different devices over Wi-Fi, some Internet of Things maybe, mix of multiple technologies. But first thing we do, obviously, we need some sort of a build. So build Mark 1 has two targets, make clean and make image. What do you think about such a build? Anyone? Good, bad, missing something? Yeah, first of all, release the bug, definitely. But there is something even simpler, maybe. Thank you. No unit test. There is no target here for unit test. So what can you expect about this project, right? This will be hell of a crap, right? No unit test at all, a lot of binaries, and obviously testing everything on a hardware. Wow. Okay, so let's try build Mark 2. Okay, we have unit tests, so it improved things a little bit, but already a colleague noticed, yeah, but the bug release would probably be a good idea as well. So in a way, adding this tests actually gave us a false sense of correctness, right? Like having this oar tied with the rope to the wagon, right? It didn't really fix a problem, right? We're just a little bit closer to it. So scratch that, we definitely need a plan. So we really need to think, what are our requirements here? So let's think about build options. What actually build should provide? We'll divide them into two sections, the core ones and the nice-to-haves ones. So core, obviously, debug, release, right? Another thing, some sort of set of targets. So we would like to build target software for the platform, some tests. When it comes to tests, it might be like unit test, module test, integration test. We might have different target for these. Also, an architecture, at least two. First will be like our target hardware, let's say ARM v8, and the other one AMD 64, so our workstation that we work on. We would like to have our code, also the production code, to be compilable and runnable on our PC. We'll talk about how to do it later. And some nice-to-haves. Well, sanitizers. We actually have, this year we have an expert on sanitizers, Chandler Carrot, so you can actually consult him when it comes to details, but basically you would definitely want to see if we are not going out of the bounds when it comes to access. Do we have some race conditions in threads, memory leaks, and stuff like that. So definitely a good option. Since we are doing tests, it would also be nice to have a coverage to actually see if our tests do test what we expect them to test. And last but not least, permit warnings. While it's not maybe obligatory, and I personally do consider warnings as an error by default, I still like to have an option to turn this off from time to time, because when we are doing refactoring on some base component for a huge code base, it actually might be cumbersome to fix warnings that you already know that are there, but they are okay, you're fine. You are just testing this little part that you do not want the whole build to collapse because of it. And for a day or two, you actually might want to leave it as. Okay. So we have it defined, and this is where we come to rule number one, orthogonal build. All the build options should be independent of one another. So we defined this set of options, type, set, architecture, and so on, and we would like to be able to change one of them at a time without affecting the others. So for instance, we might be doing tests with sanitizers or without, in the compiled tests in release or debug mode, depending on actually what do we want to test. And we have two types, up to two sets. Architectures might be two or more. Sanitizers, four options. Coverage is like on-off, warnings on-off. If you do the math, you will actually notice that we just generated a build that can produce around 500 different results. And you might say, okay, why would anyone want to have a build with 500 different possible targets? And I say, it's all about the freedom. Actually, you do what you want, right? You have a build and you ask it to do the work and provide you the binaries. And even though that most of the time you will be just probably using like 5 or 10% of its possibilities, it's still there for you to use it once you need it. And even though that 99% of the time it might actually look like a little bit of over-engineering, that actually it also allows you to do a very smart thing, like this zero-waste bread cutter. For instance, to give you some real-life examples, you might actually want to have unit tests run on the actual hardware. And frankly speaking, this saved my butt at least twice, because I was actually hitting a bug which was only reproducible on a certain compiler, and this was compiler for the target platform, not the compiler that I have on my PC. So another example, you might actually want to target software to be running on your PC with certain restrictions, but we'll talk about it later. So having this in place, you can actually do a lot of interesting things that can improve your work. Yeah, and when we do this, implement it, we'll have this nice command. Build command, type debug, set production, architecture MIP 64, and sanitizer address, coverage true, permit warnings true. Right, cool. No more than 60 meters. Probably not even 150 characters. Everyone would like to type it like 100 times a day, don't you? Yeah, okay, so obviously something's wrong. What do you think? On one hand, we want these options. On the other hand, we do not really want to type this all the time. Any suggestions? Yeah, precisely. Let's provide some default values, right? Because, well, let's be honest, how often you manually enable coverage? How often will you disable warnings, right? So most of the time, you will actually be good with the default values. And this is where the rule number 2 comes. Easy build. Build should be easy to use. Any required complexity must be hidden inside. So, first thing, obviously, all the values should have a default value. And the second thing is, if there is any magic required to set up your SDK, push it to the build as well, not to bother developers about it. The build should be as easy as possible. In perfect solution, this should be like one command being run if you are using CMake, make it 2, and preferably without any extra parameters for the most common scenarios. And defaults should always be for developers. If you make developers type 150 characters to do their build, they will die in front of the keyboard, or you will die in front of yours. Depends. So definitely target them, not CI, not tools, developers. And what developers do or should be doing daily, mostly, when it comes to coding. Thank you. Thinking, yes. But once we do the thinking and we actually need to implement something, where do we start? Tests. Yep. So probably a good default, this is just a suggestion, but probably a good default actually will be to build tests on the local platform. So that this should be the most common case. You change something, you have a test for it, you build and you run tests automatically. Like, click, click, okay, we have click, click, okay, it works, right? So this will be the most common situation, and this is the one which probably is the worth optimizing for. Yeah. And even though this this talk is mostly about concepts, so I try to avoid talking about tools, I would like to mention one thing at the end of the build section, because most projects, embedded projects, actually use either make or CMake plus make combination. But however, there is one more interesting choice: CMake plus Ninja. How many of you know Ninja build? Okay, cool. Probably around 30 people, maybe more. Okay, Ninja is actually a nice replacement for make, which actually doesn't carry any legacy crap which make does. I don't know if you know, but when you have some targets in make, it checks, for instance, if this is not a Fortran program. If you actually start make with all the debugs to show what is actually happening, for the simple task, you will notice like 2 screens of possible tests. And this actually slows things down. You can actually do it much faster. And this is where Ninja kicks in. Ninja has absolutely no automated targets, like target deducing. No, everything needs to be written explicitly. And obviously, this is a pain if you do it manually. But on the other hand, if you have a generator like CMake, voila. And to give you some numbers, in project I currently work in, it actually takes 4 seconds for make to realize everything is built, our targets are up to date, and nothing needs to be done. On the other hand, when we switch to Ninja, one more switch to CMake, we actually have this down to 40 milliseconds. So 2 rows of magnitude gain. Quite a win. Give it a try. It actually speeds up the compilation as well, because it doesn't require so much time to check for dependencies. Okay, so 2 things to remember out of the build section. First, orthogonal builds, so we change parameters independent from one another. And the second thing, make sure your build is easy to use. It's human-friendly. You check out the repository, run one command, and off it goes. You have built software. Might be the tests, but you have built something to start with. OK, now let's talk a little bit about components. Looks familiar to you? Dependency diagram? Yeah. OK, any comments on this? What's wrong? What went wrong here? Everything, yeah. In a way, actually, probably somewhere around this is a problem. We have a lot of interdependencies and components just like depend on one another, and probably everyone to everyone somewhere around here. So we have just this enormous mass of dependencies inside. And this is actually a classic facepalm for the design. Just too many dependencies inside. If you think about it, this is an IT equivalent of do not touch any of these wires solution, right? Just too many dependencies. No one actually is knowing what is happening behind there. And if something breaks, then we should probably fix it, right? So, no. But there's more. There's time to link it, right? I highlighted in red the most important part, but probably you cannot see it, so let's zoom in a little bit. And here we have this start group and end group. This is a very old school of linking, but still quite popular in embedded projects. How many of you know linking groups? Whoa, 3, 4 people maybe? OK, so when it comes to regular linking, it goes like this. We have some main, which has dependencies to other objects. So we passed linker a set of libraries we want to link against. Linker checks the library, resolves all the symbol that it was missing, and adds the new symbols for these libraries which are still undefined, and proceeds with next library. Resolves some symbols and add new undefined. And it goes up to the end of the command line. Once it reaches the end, either you have a working binary, all symbols have been resolved, or you have a situation where some symbol has not been found in the library and this is a linking error, symbol is missing. And that's it. And someone realized that, okay, but if we actually make a circular dependencies between the components, so A depends on B and B depends on the A, then we actually have a problem because we need to put these libraries multiple times, twice at best, but probably more, into the linking command in order for linker to resolve all the symbols correctly. So someone came up with idea, okay, so let's actually consider this a group and tell linker, look for the symbols inside this group as long as possible, just to make sure that finally we find it. If we checked all the libraries and all the symbols and haven't found it, then, okay, we signal the problem. So let's do the math. So we'll have G groups, M dependencies per each group or library, and we have, oh my god, complexity. Actually, if you multiply this, this is n squared, and I think this is how mammoths die. They were using n squared linking, and actually they just starved to death in front of their computers, waiting for build to finish. I personally once worked in a project where it took around 20 minutes to do the from-scratch build of everything. This was quite a big project, and then it took 3 minutes to link. Think about it. 3 minutes of linking. You're doing a little tiny change in this little library, which compiles in half a second, and then you wait 3 times for it to link. Something went wrong, right? So the rule number 1 regarding components is dependency tree. Dependencies of each component must form a tree. So make sure it's just plain and simple. There is a main, there is a component 1, component 2, main depends on these components. They might have a common set of dependencies like component 4, that's fine. Problem is if component 4 depends on component 2, because then we have a cycle and then we fall into the trap of linking groups, which makes it incredibly long. So please hug the trees, make your work environment green, save the forest, and everyone will be happy and stuff like that. So just make sure your components are always forming a tree. Now, another classical example. You're joining a project, you're having a look at some source, and you would like to see where actually this includes belong. This is the part of the component, maybe something from the outside of the library. Where would you start to look for this includes when seeing the file? I would have a look at the compilation. So the command line for the compiler. So let's copy and paste it on the slide. And for your convenience, I highlighted everything that is important in red. So you usually then see all the includes libraries of all the projects, wherever it goes, and it's all squeezed into one single command line. My personal record, the compilation, the command to compile actually was 1 screen long on a really, really big LCD. So this is probably the first signal that something is wrong, right? You look at it and so big. No. There is a problem. And in fact, there is. If you think about it, you now might have actually non-unique file names. So you might have a foo component with writer HPP file and a bar component with writer HPP file. Sounds scary? Let's go further. Actually now, include of orders does matter, because what actually include writer HPP means? Well, it depends, kind of, because if you first include foo and then bar, then writer HPP will obviously be foo. But if you do bar and then foo, then writer HPP will be bar writer, right? Sounds interesting, but it actually gets even funnier, because you have these 2 components that up until now were independent, and then you created a fizzbus component which requires a dependency towards a foo and towards a bar. And guess what? You are unable to come up with a reasonable set of flags to compile it, because either way, you will always hit this writer or this writer, and you're in deep problem. So definitely not the way to go. But some people still think they can actually cheat the system. They can underscore it with the name of the component. So we can have foo/foo underscore writer HPP. Bar, so then bar underscore writer HPP. That's cool, right? No. No, definitely, this is not the way to go. So rule number 1 is about namespace segregation. Keep files inside directories named after namespaces they contain. Each file is named after class it contains. May sound complicated, but in fact is that simple. Let's have a look at an example. So we have a class named writer, which is located in the namespace bar, which in turn is located in the namespace foo. So we map namespaces to directories, foo and bar, and a class name to the file. So our header is foo bar writer HPP, and implementation is foo bar writer CPP. And that's it. You always see the class, you know the namespaces, so you know exactly where it's located. And because you usually call the namespaces after the components, this actually is a component directory. So it's very simple. It's very easy to understand, very easy to follow. And actually, right now, you'll have just one single include into your project. Because that's all it takes. You just need to point to the root of the project, and then all the paths from that point on will come on naturally. And now, thanks to the file system, you will never have a collision on file names. Because if you have a collision and you will try to create a new file that already exists, you will actually open a file that exists and you will see the content, right? And if you create two writers in two different directories, this means that they will be in a different directories, so no problem on a file system level. And since the directories differ, it also means the namespace differs, so there is no collision on object level as well. So that's simple. No problems from that point on. But whenever I introduce this rule in the project, someone comes and asks, OK, but what about private includes? I mean, each component has some includes and that it needs to use for internal purposes, but you definitely do not want to signal anyone that this is a public interface. I personally used Boost detail convention here, which is used by Boost. And the idea is very simple. If you have something that, for whatever reason, can, technically speaking, be included by someone or used, just put it into detail namespace. And according to our convention, let's put it into detail directory as well. So effectively, we might have a component with two public headers, the interface, foo public HPP and foo interface HPP. And then if you want to have some internal implementation, you just add a detail here. Detail namespace and directory, and then some internal HPP, do not touch HPP. And this is actually very easy to follow. So actually, for all the projects I worked in and we had this rule applied, it was just enough to do the code review. So during code review, you can clearly see that you are including something from the detail namespace of the other component. It really strikes eye. So basically, it's just enough to do it as a part of the code review. The rule will be followed. If you have really big project and you want to be super sure that never happens, you can also create a shell script of probably 3 or 4 lines to check each component if it doesn't include something from the other components. And you can actually make it as a part of your CI run. So for each commit, the rule will be enforced by the tool. You can do this, but frankly speaking, most of the time, it just works out of the box. OK. So 2 things to remember out of the components. First, dependency tree. Your components always must form a tree. This is first, avoid a linking and square linking. And the second thing, it actually keeps your architecture clean. So if you're on a good side of the force, you'll probably, it will just come up naturally. And the second thing is namespace to directory mapping. So whenever you have a namespace, make directory out of it and put files inside, and files are named after classes. So we have one-to-one mapping here. OK. So now let's talk about how. I promised some embedded. So whenever embedded developers talk about portable code, they usually mean something like this. Please do not read it. It's really not important. It's like copy and paste from some random project open source. Instead, I would like you to have a look from a distance. So the dominant color here is preprocessor, right? So actually, if you count the lines, almost exactly half of the lines here is preprocessor, right? So just by looking at the source, you know you have seen it before, and you're almost sure it shouldn't sound like this. So something went wrong along the line. And here, let me quote Steven Durst here from his excellent book, C++ Gotcha. Quote, I have to use a preprocessor if-def statement to handle the different platform requirements, end quote. To prove your point, such as it is, you display the following code. Some portable code, if-def platform A, do platform A specific stuff, and if-def platform B, do platform B specific stuff, and if. The conclusion. This code is not platform independent. It's multi-platform dependent. Any change to any of the platforms requires not only recompilation of the source, but change to the source of all platforms. You've achieved maximal coupling among platforms. A remarkable achievement, if somehow impractical. Nothing to be added here, I suppose. So the rule number 1 for HAL is don't use if-defs. When you are using if-defs, you're definitely doing something wrong. But embedded developers, please don't panic. There are techniques that actually can circumvent that, so we can have really portable code with nice separation of concerns without using preprocessor. And it boils down to providing a proper set of abstractions and a little bit support from build. So about the HAL itself. HAL stands for hardware abstraction layer. So it's basically the lowest part of the lowest layer of your system. There is a component that actually directly talks to the hardware. From this point on, there should be straight line, and above it, there's only a business logic. So we have a clean separation of the code that is platform dependent from the business logic that is above it. Please, however, note that HAL is not a recursive acronym. It doesn't stand for HAL abstraction layer. So if you have like HAR over HAL and so on in your project, please fix that, and then we'll proceed with the remaining parts. So having this said, let's talk about hardware abstraction layer. Let's first start with a little quiz where actually HAL could be useful. Let's have a look at a few examples. First, good examples, init LCD. This is nice, right? We just say we want to initialize an LCD, and we really do not care if this is like LCD connected to the big computer, or maybe this is like 2x16 little display which can display only characters and is connected to our microcontroller. So, sounds reasonable. Then, a back key pressed, returning bool. Okay, again, quite abstract. Actually, this might be an on-screen button, on a touch screen, we can click it with the mouse, or maybe this is one of these big red buttons for the oh shit moments, right? You do not care, right? You just check if the button has been pressed. Again, reading from serial port and returning 1 byte. Okay, we do not really care if reading here actually means manipulating registers, or maybe there's some queue internally done, or maybe we're using a syscall for different platforms. It doesn't matter. We are just reading 1 byte. Some bad examples. Read status register returning int. Yeah, okay, cool. Now, can someone tell me how do I interpret these bits? Yeah, I cannot either, right? So probably there is a problem. And most likely, even if someone will actually come up with a reasonable definition, the new platform will arrive and we'll be back to square one. No way to go. Status line 15. Okay, again, any help from the room? Yeah, I suppose so. I also do not have an idea what's the status line 15. And port A, return 1 byte. Well, that's super obvious. Until you actually change a platform, and this will be 2 bytes. Or until you get a new hardware, and actually stuff that was usually connected to port A is now connected to the port B. So now will you rename it for one platform or for all platforms? Or maybe you'll just remember that actually port A is port B on this one particular hardware. Well, difficult choice, right? That life is about choices. Yeah, so we probably already see the pattern here. The good examples are all about answering what question, what should be done. The bad examples actually try to address how question, how we should implement it. So basically here we are linking abstractions, while here we are stating what do we want to do without referring to underlying details. So this will be the rule of thumb here. And now let's play a little bit with interface and implementation. So I promise to keep it a little bit tool agnostic, but we obviously stick to the C++ world. And let's say that we have our abstract component, which is called stuff. And we will like to enable stuff. So we make enable stuff HPP file, which contains just one function, enable stuff. And then we do the implementation. Enable stuff CPP, one function enable stuff, and then if dev platform A, do some platform A related stuff, and else do the platform bar related stuff and if. Any comments? Yep, exactly. What we did wrong? Ifdef, precisely. We just said that we do not really want to use the ifdefs because they're actually causing problems. And all these internal dependencies between platform co-located. So this is the code for which you get a facepalm from the polar bear. And when you get a facepalm from the polar bear, you definitely know that something is not right. So let's try to fix it. There is a technique called split backend, and it's very simple. You create enable stuff underscore name of the platform, let it be foo, .cpp, where you implement a function, enable stuff, which does only platform foo related things. And then there is an enable stuff underscore bar, another platform, .cpp, that has enable stuff, but internally performs only platform bar related elements. And the one last thing that we are missing is a build. Inside build, we add to the list of sources our implementation file. So in our case, this would be enable stuff underscore a platform CPP. So here, we actually tell the build to take a proper file for a proper platform and do the compilation. So this way, actually, when it comes to this hardware-related part, different files are selected for different platforms. And this is how we actually decouple the elements from one another. But again, if you do this this way, commit it to the repository, probably no longer than a few hours, maybe a few days, and someone will come to your desk and ask this famous question, yeah, okay, but what about the footprint? And I usually answer, yeah, what about it? Actually, have you measured it? Because if we do not measure, we really do not know what are we talking about. If you actually start to change the code without knowing what was the original intent, what was the original size, speed, then you do not really know if you actually improve things or make it worse. And you are like have equal chances to do both because you haven't measured. So first, let's measure. And actually, if you measure, you will notice that most of the time the solution is just good enough. Because even if you have like this little extra overhead for calling a function, I mean, how often do you initialize LCD or a serial port? Like maybe once at the program startup? You might say, okay, but I'm like reading from the serial port constantly. Okay, but most likely you have microcontroller that runs at some tens of megahertz, or maybe a PC running at gigahertz, and then you have the serial port that pumps data in kilobytes, right? So really, not that much of a problem. But obviously, you might hit a very reasonable situation where actually this is a problem. These few bytes extra will really cause a lot of headaches, and maybe you are not making real-time requirements. So what to do then? I would first go for LTO, link time optimization. How many of you are familiar with LTO? Okay, around 30 people, maybe 40. Yeah. Okay, so just to make sure everyone's on the same page. LTO is link time optimization, so it basically says, how it works is it allows us to do certain optimizations that normally are done for a single translation unit, a single file that we compile, actually at link time. So normally, if you have two different translation units, two different CPP files, and you compile them both and link them, if there is any dependency, the linker will just pull in both files and make a function call from one to the other. But with LTO enabled, you can actually enable linker to reason about what is happening between these two files. So it actually may notice that we are doing function call from one object to another, but actually this is very, very little function. It has like 1 or 2 lines. So instead of doing a function call, we can just inline it in place. So this way, we can actually get rid of all the overhead. And this is not only the overhead inside our hull part. Actually, this will improve the whole project, because everyone might be using these little functions just to make sure their architecture is clean. And then we actually remove extra overhead for it. But obviously, we're embedded developers, so we are very often dealing with platforms that do not really support a lot of fancy features, and we actually might turn out not to be able to use LTO simply because compiler or linker doesn't support it. So then there is one more technique called split header, and you probably might figure out where actually we are heading with it. And split header works very similar to split backend, but now instead of playing with CPP files, we'll play with includes. So we have foo/enable stuff.hpp, and we have an inline function enable stuff that do all the foo related elements. Then we create a bar directory and enable stuff HPP here, inline enable stuff, and do all the platform bar related functionality. And again, we glue it on a build system level. So we just add one single flag to the compilation. Just add one more include directory which is named after the platform. And we're good to go. If someone includes enable stuff, if we are compiling for platform foo, this file will be selected. If it's platform bar, then we select this file. And we're good to go. So rule number 2 is about split backend. Separate platform-dependent implementations with split backend, split header, or a mixture of both, because you can actually use both solutions at the same time. Most of the time, I would recommend split backend because it offers clean separation. It allows you to include less when you are using these hardware-related elements, so it's good. But on certain occasions, you might fall back to using split header as well. Now, this is how we improve projects. This is how we make Polar Bears pleased. But there is more to it. Probably, if your project is big enough, you will finally get the message from the manager, okay, our clients are super excited about these features we're working on, and we would really like to have this new platform and port our code there. So how do we actually port a code to a new platform? We're using this split backend, we have this nice separation, but again, how would you approach it? My one-liner here is find repository path, name, and we are finding files matching *_ and name of one of the platforms. Let's say amd64.cpp. This command will list you all the files inside the repository that are platform dependent for this particular platform. And for all the other platforms, you will get exactly the same set of files, only this ending will be different. So now you can have a look at it and go to your manager and say, OK, we checked. We have 30 files that need to be adopted for the new platform. Each of them is on average 100 lines long. So we effectively need to write 3,000 lines of code. And taking into consideration the speed and efficiency of our team, it roughly maps to 1 month. That's quite a fair estimation, don't you think? We can actually support our claims. How long will it take with the actual numbers? We have implemented few platforms, and we already know exactly which points need to be checked. And there is more. Because once we do this, once we implement all the files for the new platform, we obviously need to test it. But what is a nice thing? Because we separated the sources, we now know that we do not really need to test all the platforms that we had supported, right? Because we have not changed their sources. We just added new sources solely for the new platform. So only thing that requires throughout testing is the new platform, the thing that we have added, which is a very good feature. But again, there's more. How many of you have heard about modules for C++? Okay. How many of you have heard it for about a decade? Yeah, this is a feature that we are waiting for quite a long time. But the interesting fact is that inside the proposals for modules, actually, most of them state that preprocessor will not be available inside the module. So either module or preprocessor. But guess what? We are actually not using preprocessor at all in our solution. Nowhere in our repository there is a single ifdef for it. So actually, this is the place where you make polar bears dance out of happiness, because you're not only having a very good solution, you're also a future-proof. Excellent, right? What a beautiful day. OK, so regarding hardware abstraction layer, 2 things to remember. First, don't use ifdefs. And if I will ask for one single message that I would like you to take out of this room, don't use ifdefs, please. Instead, split backend or split header. OK, now let's talk a little bit about testing. So whenever people are talking about testing, they usually refer to unit tests, module tests, integration tests, sometimes system tests. And this is not what I actually want to talk about. Instead, I'd like to talk about a little bit about automated tests versus the manual tests. So whenever people are talking about manual tests, they usually refer to it as bad tests, right? The one that we need to do manually are bad. I actually happen to have a little bit different opinion here. I actually think that they can work in a complementary fashion. It's actually about the trade-offs. So if you have automated tests, they're repeatable. Yeah, same input, same output, same code. They're fast because machines execute them. But they actually require a framework setup. And when I'm talking about the framework, it's usually not that bad, because for unit tests, you are like having a Google test, maybe some catch or Toot or other framework, and it's like 5 minutes of work. But on the other hand, if you have parts that are platform related, they require actually to work with the hardware, you'll probably need an emulator for your platform. And by platform, I do not mean only the CPU. I mean the platform as the whole set. If there is an LCD or a serial port, you also need to have it emulated, connected to the proper pins. So this actually might lead to the situation where you will need to write the one from scratch. And this is a significant amount of work. So probably only the biggest projects could afford that. And this is where manual tests kick in. Because even though they're slow and error-prone, because, again, humans need to interpret the result, they actually require a minimal setup. So if you think about it, when you're doing a manual test, you're just writing a small, simple binary that you put on the device, run, and observe the result. And that's it, right? So you basically require only to have a hardware on your desk, and nothing more. So in a way, if you have a look at the plus and minuses here, they are complementary. And this is where maybe not a rule, but a suggestion, number 1, comes in. The best effort. Use automated and manual tests in complementary fashion to speed up the development. And let's have a look at some examples. So how would you deal with a situation that you need to have some custom container fine-tuned for your data set, and you need to implement it, and now how many of you would implement these tests in automated fashion? Please raise your hand. Okay. How many of you would do it in manual fashion? Okay. Okay, I would definitely go for automated here. Why? Well, actually container is sort of a business logic. It's not really hardware dependent, right? So we can easily test it in memory, and we'll have repeatable tests. And if someone, because we're doing this probably due to some optimization, if someone will come in half a year and then try to optimize it even further, it would be good to have some sort of base ground to know that we are, by optimizing, we are not breaking the basic functionality. Then another serial port driver. Again, automated tests, okay, manual tests, okay, most people will go for manual. I'd go for manual here as well, because if you're doing automated testing, you actually require to have this platform emulation, which can be really a heavyweight. On the other hand, how often the implementation of in-silicon serial port changes. Once you implement it and test it, you'll probably never touch it ever again for this particular platform. So it's like a good start to do the manual tests. Now, you have some tests that requires to be run as a part of continuous integration. Automated tests, manual tests. Okay, this was catchy, but no one catch it. Okay, good. Obviously, here we need to go for automated tests because part of continuous integration means we need to run it over and over again. So definitely automated. And the last one, DMA access to the LCD buffer. So we would like to write on a screen as fast as possible. So again, automated tests. Okay, a few people. Manual tests. Okay, majority, definitely. Yep, I'll also go for manual. Why? Again, because this is actually, aside from the fact that you have an emulator, it's actually it's super hard to test it. Think about it. You are writing using DMA to some memory location, right? Okay, but now how can you tell if this is correct? I mean, what these bytes actually, or bits actually mean. And if you're having manual tests, it's easy. When the white rabbit pops up, you follow it, right? You're good. But if you see some scrambled image, then you know the test doesn't work. So you just run single binary, open a window, and then you see if your code works or not. So it's super easy to test manually. And again, you probably already see the pattern. Or suggestion number 2, hull boundary. Hull is usually just a good layer to distinguish between manual and automated tests. Whenever we are talking about hardware testing, like for this lower layer of the software, it's usually good to give it a try with manual tests. But when it comes to business logic, pretty much always we should do the automated testing. Yeah, but some notes here. First, automated hardware test. You can still have these. You might have, for instance, a reference platform connected, physical platform connected to the physical PC with a predefined set of cables and run automated tests there. It is doable. I have seen projects where it worked like a charm. So if it's possible for you, you can spare one device. This is a very good idea. If it's possible, you might be doing a hardware emulation, but as we said, this is expensive. And last but not least, the manual tests need to be implemented and versioned as well. By manual test here, I do not mean like play around with cables and see if it doesn't explode. No, we are having a hardware, we're pushing the binary that we compiled. The binary might be simple, just like initialize serial port, send some bytes and receive some bytes and print them, something like this. But then we can manually connect this real serial console to the device and see if these bytes actually get transferred. So this is what I mean by manual tests. Only the human part is interpreting the result and nothing more. So, 2 things to remember. But first, the best effort approach, so try to balance between automated and manual tests to get as much of development speed as possible, and consider the hull boundary for doing manual versus automated testing. Okay, and this said, we approach the end of our presentation, C++ style. Well, obviously, I do not try to sell you a golden hammer. So, for instance, to give you some counterexample, if you are doing the project that has 1,000 or 2,000 lines of code, you can probably do it any way you want, and it will just work, right? But on the other hand, if your project gets bigger, you will find more and more of these advices useful, and probably after reaching some point in time, you will just find it irresistible, because otherwise you will be just fighting with bugs that normally should not be there in the first place. So please apply them with care and consider them like a good guidelines and tested practices. So to summarize the whole talk, the builds orthogonal, so multiple options independent of one another, and build as such trivial to use. Components. Tree structure, so always form a tree, never cycles, and namespace to directory mapping to make sure that symbols and file names are always unique. Hull. No if-defs, ever, never. Instead, split backend and split header. And when it comes to testing, first consider best effort approach to balance, and then consider a hull as a layer of split between the implementation of manual and automated tests. Okay, on this slide I put some links for reading, but the presentation will be available offline, so we'll not be going through them. Instead, we'll try to switch directly to the question and answer session. So if you have any questions, this would be the good time to ask them.
Okay, you mentioned that we need to preserve a tree structure of the component inside our application. So, do you have any advice how to automatically preserve it? Have some automates to check if we have any circular dependencies inside our build?
Yes, the tool is Linker. Actually, if you create a circular dependency, you will just find out that some symbols have not been found. Because, for instance, the order of libraries will then cause it, when you pass the library, just let me give you an example. Library B and A. A linker goes through B, and then notice that B depends on A, so it resolves the symbol for A, but then on A it will find the symbols that were supposed to be resolved with B, but at the time the B was processed, it didn't have this information. So basically you will go through the whole list of libraries and find out that these certain symbols from B were not found.
This is quite an obvious situation, but for example, if you are using, for example, CMake, you can go to the situation where you are explicitly giving dependencies for your single component in different places, in different files. So it is easy to make this these dependencies, and just Linker will, CMake will give proper GCC command, and you will see it only if you see verbose output of the CMake.
Yeah, actually, before the question and answer, I thought like, okay, torpedoes in the water, and there's the first one, right? Okay, so it's actually not that bad, because as I said, usually when you get into circular dependencies, you would like to, you will end up having multiple times the same library put into the linker command in order for it to work. So for like maybe one single break of the rule, you actually might not notice it. But when you have multiple such places, you will definitely catch it. And actually my advice when it comes to using CMake is always state your explicit dependencies only. So CMake actually can sort of derive dependencies. So if you have like library N, A, and it depends on 5 libraries, and then you have like the library B, which depends only on A, then inside library B, just point it, okay, I depend on A, and nothing more. And the CMake will automatically deduce, okay, this is A library, and A library depends on 5 more libraries, and will automatically include them. So just state the requirements explicitly in the place where you have one single library, and then you will not have this need of like copy and pasting all the dependencies around. Okay.
Hull for other platforms from your perspective is basically unused code. So when you need to change signature, you make cause conflicts for other platforms. So any good advice on how to handle this?
Yes. Actually, when you're using split backend, please note that the header, the main header for the function, class, or whatever is always common. So actually, you do have a common place. And as a part of your CI, you should be doing at least one build per platform anyway. So if you do find there is some inconsistent, you will definitely catch it on CI.
I was wondering if when using split backend and link time optimization, you've run into any problems where third-party code is relying on the fact that something in another translation unit won't be reordered across call boundaries after inlining.
I personally have not hit this situation, but I'm aware that such situation exists. For instance, I think you have had such a bad experience with libraries. Yeah, it may happen. Actually, the truth is that most of the embedded libraries, the third parties, are written in C, and usually this is like a hard code C, like you could see something in the 80s. So yeah, this might be. Thank you for the comment, by the way. I forgot to tell about it. Yes, this might be the case. So when it comes to link time optimization, even if your compiler does support it, make sure that your third-party libraries also do support it correctly. Okay, so maybe the one final question actually will come from me. So how many of you have been on my last year's talk, C versus C++ embedded? Okay, like 20 people. Online counts as well, right? Okay, I promised to do some Vim versus Emacs, and actually I'm a Vim person, and I think that Vim is awesome because it has the neon cut plugin, so we can see the progress bar in neon cut form. But I also recently found out that Vim is addictive. if you actually type into Google how to quit, you'll get like drugs, smoking, alcohol, and VI. So please make sure you dose it correctly. Okay, thank you for listening.